it in a holographic way. I mean, we will use the gravity tool of some particular model, and we will study the chaos and the entanglement from it. So this talk will be based on our two work. The first one is with Shankadeep Chakrabarti is my supervisor, and the Karnavasil, he was a postdoc there. And the second part is based on this second work, which is with my supervisor Shankadeep Chakrabarti, Karnavasil, he was a postdoc there, and the Hironori Hoshino. Okay, so let's move. So here is the outline of my talk. So I will start with the introduction and motivation. Then I will introduce the holographic back reaction model. What is the back reaction there? Then I will compute the holographic entanglement entropy from the bulk side. Then I will compute the entanglement wedge cross section. So up to this will be from the first part, from first paper. And after that, I will go for the shockwave analysis, which is a tool to study the chaos in the gravity side. There, I will also compute the thermomutual information, which is basically a quantity which used to compute the two-sided correlation in a thermophile double state. We'll see it, yeah. And also, if you perturb the system, then what is the effect of that perturbation on this two-sided mutual information or the thermo mutual information? So we will see that. And after that, I will summarize the talk. Okay. Okay, as we know, any quantum system, either it is a pure state or it's a mixed state. So, and also a quantum system may or may not be entangled. That depends on, so for example, here I have two examples. So I can see the first, these are the bipartite pure states because I can write the psi. So now in the first example, I can separate this, the A and the B part in a cross product. That means if I measure one of them, I mean, if I measure this part, let's say for A, then I don't know which one I will get for B because both are possible. So that means they are not entangled. I cannot extract any information by just measuring the one subsystem. That means these two are not entangled. But if I take another example where I can see I cannot write this state in this form. I cannot write in this product state. So that means if I measure, let's say A, and I get the 1 here, so then that immediately tells me that B has a outcome 0. That means I can extract the information by measuring one subsystem, and I can extract the information for the another one. So that means these states are entangled with each other. So this is one of the example of the entangled state. Now, if you have a state, you can construct something called the density matrix. Okay, so for a density matrix, you have to take this product, and that is your density matrix. So if you have a mixed state, then there is no notion of the state. You cannot define the state in case of the mixed state. You directly start from the density matrix. So this we call the bipartite density matrix because it has this A and B two subregions. The property of this density matrix are that this trace of rho square AB equals to 1 if it is a pure state, and it will not be equals to 1 if it is a mixed state. So that's how you can, if once you know the rho, you can find it trace, and you can say that, okay, this is whether it is a mixed state or it is a pure state. Now, if you talk about the entanglement, so there are few measures which you can compute to detect the entanglement. For example, you can compute the entanglement entropy, which we call the von Neumann entropy also. You can compute the entanglement of purification. You can compute the mutual information and logarithmic negativity, and there are a few other quantities. For example, this discord, etc. Okay, but what happens if you have a pure state? This entanglement entropy is sufficient to measure the entanglement. But once you have a pure mixed state, then this entanglement entropy is not a good measure for the entanglement measure. The reason is because in case of the pure state, there are only the quantum correlations. Okay, but if you have a mixed state, there are quantum and classical both correlations, and this entanglement entropy or the von Neumann entropy cannot distinguish between them, and it includes all of them. So it will not consider a good measure for the mixed state case. So in this work, our focus will be on the entanglement entropy and entanglement of purification. So the entanglement entropy is defined as this minus trace of rho A log rho A. What is rho A? Rho A is actually you take the rho AB and you trace out the B part. So that will be your rho A. Okay. So once you know the rho A, then you can use this formula. This is called the von Neumann formula for entropy, and you can write the entanglement entropy for any rho you want. On the other hand, if what you can do is suppose you have a mixed state rho, what you can do, you can add some another part and you can such a way that you just trace out that part, you will get the rho A back. This process is called the purification. And there are infinite number of ways I can add different subsystems. I can just trace out them and get my original rho A back. So what happens basically, what you are doing, because we know that it is easy to work with the pure state. So we somehow purify our mixed state and work with that state, and at then we just trace out the remaining part. So this process is called the purification. Now the measure entanglement and purification is basically depends on all possible combinations which you can add, and you choose the minimum one of that, the minimum entropy for these subsystems, and that will be your entanglement of purification. So for example, you have some rho, you add some extra part, and then you construct a pure state, because now you can remove that extra part and you can get back to your this rho A back. Okay, so you choose minimum combination which has the minimum entropy, and that will be your entanglement of purification in that case. Okay, now if we want to study these entanglement measures for a strongly coupled field theory, so we know that it's because of the non-perturbative behavior, you cannot do anything on these strongly coupled field theories. So how to do that? So the way is you use the ADS-CST correspondence, you work with the dual of those strongly coupled systems, and you compute these measures there and relate the for the strongly coupled field theory. Sorry.
So since I'm not quite familiar to the purification, so you said that we have to take a minimization of the entropy.
Yeah.
But how do we know that the state is a kind of minimum, realizes minimum? Okay, I can imagine that suppose that we have some system, then we will put some extra space, extra state to make a purification. That okay, I guess there are many possible ways for purification.
Yeah.
Then how do we know this is the minimize the state or not? I mean, okay, so suppose that we have 10 candidates.
Okay.
I can say that, oh, this guy is a minimum. But I'm not quite sure if this is really a minimum among all the possible kind of extensions.
So what happens? You have some rho, okay, and let's suppose you have a rho AB, which is now or mixed state. Okay, there is something which you can add in rho AB, and that make this whole thing as a pure state. Now you extract that extra part, and you can get back your rho AB, right? Now suppose I that extra piece is actually A prime B prime. So what I can do, I can get back this rho AB by tracing out these extra pieces here, which are rho AB and rho from here. And now I can define the entanglement entropy for you understand? So okay, you have rho A or A and B, and you define A prime B prime, which are actually big for the purification. Now this whole thing is a kind of pure state. Now you can write the density metric as this K chi brashi in this way, and you trace out these two parts and the entropy of this one, this A with the rest of the system, the complement of A actually. So that will be your purification in that sense.
You said that minimization is taken overall size. So
over all possible this A prime B primes.
Yeah. So yes. Then I have to choose some particular A prime and B prime that realizes the minimum entropy, right? then how can I find the A prime and B prime?
Okay. Actually, yeah. I think here it is little bit. I mean, it's not clear because it is just the definition right now. But if when we see it from the bulk sides, and we have a specific minimization there. So there it is explicit that you have a kind of surface, you minimize it, and that will give you the entanglement of purification. So yeah. So of course, yeah, there are infinite number of choices for the purification. Yeah, that's true. That's true. It's true. Okay, so here our system is a large and strongly coupled field theory at finite temperature, and there are heavy static fundamental quarks which are bringing the back reaction into the system. Now the question is, what is the effect of these large number of quarks on the entanglement measures? For example, what will happen if you take a large and strongly coupled field theory and you put large number of quarks there and consider the back reaction? So what will be the effect on the quantities, for example, on entanglement entropy, mutual information, or entanglement of purification, etc. So far this back reaction was not included because there was some probe and they work in the probe approximation, but there was the assumption that the back reaction will be neglected, but we include this back reaction in this way and ask what will happen, what is the effect of this back reaction on those holographic measures, whether this back reaction will increase it or it decrease it, or what will happen, or it doesn't affect at all. Okay, so that is our goal. So in few occasions by this K. Jason and Bannon, Prem Kumar, they have studied few kind of back reaction, but there the back reaction is because of like they choose different shapes of the entangling region, and that's how they deform their regions. Okay, but here in this case we have some explicit back reaction from these fundamental quarks. Okay, so now we cannot do anything on the field theory side. So what we will do, we will first construct the holographic dual of that model where I have a large and strongly coupled field theory and I have the n number of quarks. And now how to construct the dual of that? So consider a d+1 dimensional gravitational action. So in this action, this is the usual part. Now this Sm, which is the matter part, which I can write in terms of the Polyakov action. Okay, because this system is actually motivated from the D3, D7 plane, and the end of the string, which is connecting D3 and D7, are actually realized as the fundamental quarks because they transform under the fundamental representation. So in this action, this matter part of the action, this Ti represents the tension of the ith string, and this H alpha beta, it is the intrinsic metric of the string on the string wall sheet here, and this G mu is the target space time. Okay. Now what you do, you vary this action with respect to the background metric, and you end up with this Einstein equation. Okay. So here you can see this is the kind of picture for this, how on the boundary this z equals to 0 is the boundary and this is horizon, and here you have the singularity of the background. So here these points are actually analogous to the quarks, and each point is connected with a string because the holographic dual of those quarks are actually the strings which are hanging from the boundary to the horizon. Now the question is why they are only in this direction, why not in this direction? Because that depends on when you solve this, when you vary this action, you can choose a gauge in such a way that it positions in the radial direction. Okay, now this similarly you vary the matter part and you have this energy momentum tensor. So here you can see there is a d-1 dimensional delta function which are basically coming because of the position of the string. At where there is a string, so there is a delta function to specify the position of the strings. I can combine these parts and these parts, and I can write it as some b with a function of x. Okay, so this will be characterized or the density of the strings now. So I can, from here, I can take the average, a d minus one dimensional average over this volume, and I can write some b tilde, which will be my t. So this is now, so because I'm taking each strings are identical, so there is no need for ti. So I just have t, and there are n, okay, which is the number of strings, and this d minus 2. So now you see, if I take very large number of quarks, because I don't want to break the symmetry, so I have to consider the very large number of quarks. And then this d minus one dimensional volume will also goes to the infinity, and this ratio of n by v is actually finite. So here, the point is now this density you can consider as a constant, but still this is not a dimensionless quantity. So what we can do, we can define a quantity, let's call it B, in, and just combine this quantity with this ADS radius R, so which I will introduce. So this is not the ADS radius, the usual notation in the Einstein equation. So you can combine, you can take the product with some length scale, so that you can construct a dimensionless quantity, which we will do here. So now you will end up with this solution, this d plus one dimensional solution of the Einstein equation, which we call, which is actually the ADS black hole solution. But here you can see that now this blackening function here, so this blackening function has this density of strings now. So now this solution is not exactly the ADS black hole, but some deformation is there. So we can call it the deformed ADS black hole. And it is important to note that this dependency is actually z to the power d minus 1. So, and here you have this z, right? So if you take z goes to 0, this one will go more faster than this one to 0, right? And that we will see in the entanglement entropy results, that how this affects there.
I have a few
Yeah.
questions.
Yeah.
So now you are smearing many strings.
Yes.
I see.
Yes.
And another question is that, okay, if we are based on the superstring theory, then the fundamental string has a charge for NSNSP field, right?
Yes.
So are you also taking into account the back reaction?
No.
Okay, so you just, okay. In that sense, perhaps it's is it equivalent to have kind of a cosmological constant? Because now we have infinitely many strings.
Yes.
Then we have, okay, that energy momentum is just smeared. So that sounds that now we just put some smeared kind of energy.
Yes. Yeah, that's true.
Then the cosmological constant will be deformed. Is this right?
So actually,
Or something.
it's like you have the cosmological constant there, but on the top of that there is a deformation which is coming from the presence of the strings. Now I'm not sure whether I can say that it is kind of you are deforming the cosmological constant, but it's a kind of smearing of a large number of strings. Okay. So now, so from here we can calculate the Hawking temperature of this metric, which is this one, and we can see that this Hawking temperature has a contribution because of this B parameter here, which is the string density parameters. Now it is convenient to define this quantity as some constant, some dimensionless constant rho. And for the future discussion, it is also beneficial to define T, the effective temperature, in this way. We will see why we are defining it, because you will see the definite dependency on this TF because of this definition. So this is just a redefinition. So now we will compute the holographic entanglement entropy. So to compute the holographic entanglement entropy, we use the Ryo-Takagi prescription, which says that you compute the area of a minimal surface, which is actually homologous to that region on the boundary. So we have some region A on the boundary, and there is a homologous surface, which is, and you minimize that, and that the area of that will be actually the entanglement entropy with the rest of the system. So the pictorially you can see this one. So this is our region here, and this one is the RT surface, which is moving into the bulk. Sorry, this is small l by 2 because this direction is basically x direction, and this is the y direction. So you fix your y, all the yi directions, which are actually the other d minus 1 dimensions, d minus 2 dimensions, and in a particular direction you can fix this in, let's say, in x direction. You have the regions defined on minus l by 2 to l by 2, which is this one. So this is not capital actually. Basically, this is minus l by 2 to l by 2 in this direction because this is the x direction. So in that sense, you have your RT surface in this one. One important point here is actually this point will be, so here, this point, yeah, this point is actually the turning point of the surface, because after this point, the surface is coming back towards the region A. There will be divergences because of these parts. So I mean, which are usual for the entanglement entropy calculation. We will see that there will be, we have to define a cutoff so that our expression will not diverge. Okay, now how to do that? So we have this metric. Okay, we can define our RT surface in this way. Now we have to compute the external, I mean the area of this external surface. To do that, what I will do, I will first compute this. Sorry. So I will compute this induced metric, right? And then I can compute the area of that induced metric, which will look like in this way. So here, this factor, I can this whole thing is kind of Lagrangian. Okay, and we can see that it doesn't depend on the x. So there is a conserved quantity corresponding to that x. Now I can use the equation of motion. I can compute that conserved quantity, and so from there I can find out this dx by dz, and I will substitute it back in this expression, and I will end up with this sorry, yeah, I will end up with the okay, so this, yeah, okay, so I will end up with this expression. Actually, I will define what is the u here. Now using this conserved quantity, what you can do, you can find this dx by dz, and that dx by dz helps you to build a relationship between this width boundary region L and the bulk parameter, which is basically the z, this radial coordinate. And if you just take it in this side and integrate both of side, because your x is running from minus l by 2 to plus l by 2, then there will be an integration over x, and then there will be an integration over dz, and you will end up with this relationship. So here we have small change of variables. We define this u as z by zt. So now at the turning point zt, this u is equals to 1. And if you are on the boundary, that means z equals to 0, then u is 0. So that's how you can see the limit, this one and this one here. Okay. So there is small change of variable from here to there, just for the numerical purposes. Okay. One can plot these two, and you can see for different dimensions, these are the behavior of the RT surfaces here for different dimensions. So higher the dimension is, the RT surface moves more into the bulk, because you see, and it moves more faster. It's more steeper from the boundary here. You can see. So it is plotted with respect to the region of the boundary region.
Excuse me, what's the definition of dimension? A dimension of the full space-time, or some region of the A or B? And you said the dimension.
Yeah. So we have D plus 1.
Okay.
So this D is 4. Let's say you can change it 4, 6, 8.
Okay. In the field theory is on D.
No, D. Yeah, field theory is on D. Yeah.
Okay. So
Field
you are
theory.
talking
One less dimension. I'm talking about the, yeah.
In the bulk.
Right. Yeah. Because this RT surface is basically the codimension 2 surface. You fix a time slice. So that's how you are reduces 1 dimension, and then the rest of the dimension, it is like it is for example, this radial direction z is a function of x, the boundary parameter. So like it's moving into the bulk. Okay. So this S is actually the from here. You see, I can substitute this area here, and I can compute the entanglement entropy. How can I do?
I will make just a comment in Japanese for students. これ南部語とさ、だけどストリングのワールドシートじゃないんだけど、時空上のなんかある条件をはめた最小面積を計算すると、ある種のエントロピーが計算できますっていうのを計算する。
それがそのさっき言った流高値の公式の。
で、そうそう、ミニマルサーフェスを計算するときに、今日のエリアと同じなんで、南北国作用じゃないんだけど、
それがちょっと D とか入ってる。
で、スクエアルートとか大体そういうやつのこれです。Because in the morning we talked something on the minimum area or Nambuto action. So this is I made some comment in Japanese for students.
Yeah, so square root G action number. Yeah, right. Okay. So similar to this, okay. So the relation between this the entanglement region width and this bulk parameter. Here ZT is actually the turning point of the RT surface, which I have shown here. This is ZT. Now you see this change of variable I can also do here, and I will end up with this this kind of entropy. So this will be the formula for the integral form of the this entropy formula. Now, from here, it is not possible to directly solve this integral. I mean, now the question is what to do. So what we can do, we can use the Euler's beta function, okay, which allows you to expand this part here to this part and write it in terms of the summation form. So that's why you can see here summations are here. So there is some, some well-defined beta function, and you use that beta function formula here. Then you have some expansion form of this integral, and then the integral inside will be doable in that sense. Okay, so you can see it is running from n equals to 1 to infinity, and the k is running from 0 to 1. So this part is actually correspond to n equals to 0 part, which I have separated from here. So initially you have the whole summation from n equals to 0 to infinity, and then k equal to 0 to n. But then I have separated this part, which is correspond to n equals to 0. And this part is actually, you can see there is a cutoff I have defined, which is coming from the this connected boundary regions, which I was saying. So there is some a UV cutoff. This part is UV cutoff. Okay, so this first piece and this the subleading piece and this piece, which now depends on this rho, because you see, remember this rho was proportional to B. So instead of talking about B, now we will talk about the rho, because rho is here is some relative of this string density. So this part is, of course, doesn't contain this rho. Okay, so the correction you can see from here in this part of this area function. So rho is coming here now. Similarly, you have this this expression here. You can also do the Euler beta functions expansion here, and you can write this length and zt from from that integral in this way. Now this is done, right? Because now you have a specified area function. You can define the entanglement entropy, but our entanglement entropy should be in terms of the boundary parameter. And here we have the bulk parameter, because this zt is the bulk parameter. Now somehow I have to use this relation to write that zt in terms of the boundary parameter, which is L, width of the subregion. Because you remember we have this boundary parameter is this width L, which is minus L by 2 to plus L by 2. If you change that L, then your RT surface was, increasing and decreasing, that depends. So to express this relation in terms of the boundary parameter, I have to invert this relation. But that is not, that's a very difficult. I mean, at least we couldn't do that. So what we can do, I mean, it is, you can see how non-trivial it is to invert this relation, because here you have rho and you have to write this whole thing in terms of this L by L, right? So now what we can do, So here this alpha parameter is defined in this way, zt by zh, some redefinition of the parameters. But one thing we can do, we can explore in a particular limits. In particular limits of temperature, or you can say length scale, you can invert this relationship. And in those limits, we can study the entanglement entropy. We can write this entanglement entropy totally in terms of the boundary parameter. Okay, so those are actually the high temperature limit and the low temperature limit. What do I mean by the high temperature limit? So trivially, the high temperature means if your turning point of the RT surface is very, very far from the horizon. That means here, you see, consider, so if you have horizon here, okay, and this is the turning point of the RT surface. If you take a region very small, right, then it will be like this. So this turning point is very far from the horizon. Okay. And if this region is very big, in that sense, this surface will move very close to the horizon. So that's how I can define my high temperature and low temperature limit here. Sorry. Yeah, here. So you see this ZT is very, very smaller than ZH, or alpha, which was ZT by ZH. So if ZT is very small, then alpha has to be very small in that. Okay, so the high temperature means either you can say in this way or in this way, or this is from the boundary perspective, because this TF was the effective temperature. It sets a length scales, and on the basis of that length scale, you can define whether you are working in a high temperature limit or the low temperature limit. So for example, here you see that the RT surface is very close to the boundary or very far from the horizon. That means you have a smaller width. Okay, and if it is smaller, then this part has to be very large. Okay, so this TF is very, very small in comparison to this temperature scale. So we call it the low temperature limit. Okay. Now in low temperature limit, what you can do, you can invert these relations and substitute it back here and divide it by 4G, and you will get this entanglement entropy expression in the low temperature limit.
So for the divergent term, there is no B dependence.
Yes, that is the universal piece.
So are you taking the one-by-NC expansion, or so why? What is the reason why we don't have any B dependence on the reading divergent part?
B dip.
You put some force,
Right.
yeah, to the gluons systems.
Mm-hmm.
Then you are taking the back reaction coming from quark to gluons. But this result says that the divergent part should not be affected by that kind of thing.
Yes.
Why is it the case? Do you have any quick explanation about that?
Okay, so the point is from this integration. So if you write this x prime here, then you can separate this integration by setting a cutoff, which do not include the contribution of the quark part, and that piece is completely defined in a independent way. So that result, actually, this one.
I see. So the presence of the string does not affect the geometry at very close to the boundary.
Yes, exactly.
Oh, okay. So in the language of gravity, maybe I understand. But so do you have any explanation in the language of field theory? It's because of the largency, or I'm not quite sure.
Yeah, it's of largency, but this is the universal divergence term, which which is independent of this the intrinsic parameters.
Okay, so in the language of gravity, then yeah, I understand.
Yeah.
Okay.
But okay, in terms of the boundary theory, I mean, okay. I think it's okay. In the boundary theory, this UV became the IR divergent.
The presence of okay. The results say that the presence of bulk does not affect the UV divergence.
UV divergence, right? Yeah,
So the
but
question is
the
why?
question is why? That's actually this piece is actually clearly if you to break this integral just by setting this cutoff here. So
When you say UV divergent, is it due to the epsilon on the denominator?
yes, epsilon goes to zero. You
I
can
see.
see that. Yeah.
Okay.
So you
I
see
think-
here you have zero from the limit from zero, and there is this u or ut minus one. So it's divergent at zero. This expression. So you have to
as u goes to zero, you take the
some So you have to define some cutoff,
cutoff.
and then you
So
solve.
the UV pattern cannot affect the physical final results, right? I mean,
Yeah,
the
yeah.
final- So are you talking about that?
Okay, let me make just some comments in Japanese.
Okay.
これは完璧に古典的な計算なんですけど、場の理論の量子論を含んでいるっていうコンジェクチャーなので、デスキンで出てくるウルトラの発散
っぽい。
ウルトラの発散がそうこっちにも出てくるんですよ、古典の段に。それがイプシロン。
次元政策っぽい形ですよね。
ちょっと体積減らすからね、時空の。ここまで時空伸びてるやつを、ここで寸止めするんですよ。そうすると発散が止まるんで、5次元だったやつを、なんか、5次元なんだけど、ちょっと体積減らすっていうことをやる。っていうことです。ただ、振り込みはここはやらないです。発散しっぱなしです。Okay, thank you very much. Yeah, we are talking about.
Yeah, I think I need to think about it. Why what is the meaning? I mean, why it doesn't affect the this divergent piece?
Yeah.
Okay. Okay, so this was the low temperature limit. So in low temperature limit, you can invert that relation between L and ZT, which is the running point, and you can express your result totally in terms of the boundary parameters. So here you can see now I have the result in terms of the TF and N, which is now the boundary parameter. So this is the result in terms of the low temperature limit. So now you see this term here, it is this first dependence on the rho, which is our string density here, right? And this depends, the temperature and the width dependence is d minus 1 here. These S0, S1 are actually some constants which are totally depends on the dimension, and you can just choose a particular dimension. They will be like a constant here. Okay. So yeah, so this is the usual divergent piece here, and this rho dependence is coming from here. So now you can see that this, if you increase the rho, this term will increase. So here is a leading order correction in the low temperature entanglement entropy because of this string density. So this will show an increasing behavior with rho. And if you remove the strings, all the strings, that means you take rho goes to zero limit. In that limit, you will see that this result will exactly reproduce the previous results, which are obtained by these people here. I mean, Kundu and Fessler. Okay. In the temperature terms, this dependency is the TF to the power D minus 1, and here it is TF to the power D here in this direction. So usually in what happens, their result, they have this dependency D minus 1. The leading order correction was the D actually in their result. But in our result, it is D minus 1, and that is because of this Z to the power D minus 1 term in the metric. So in the metric, we have this dependency here. With where we have this quark density, there is a D minus 1. And since if you take Z goes to zero limit, that term dominates over the z to the power d terms, and that's why the contribution is expected here from this way. Okay. Now let's see the high temperature limit. By high temperature limit, I mean when your turning point of the RT surface is very close to the horizon, or you can say that alpha, which is ZT by ZS, goes to 1. So, okay. So in this case, the problem is you cannot solve these integrals. These both integrals are divergent. But what you can do, you can construct a quantity which is difference of these two integrals from this area functional and this length, and that will be a finite quantity. In this way, I can construct a quantity and I can define an holographic entanglement entropy, which looks like this, where the rho dependence is all hidden here in this S tilde, which has this form. But you cannot do nothing much more. So what you can do, you can just numerically plot this guy for different by fixing different constants. And we have seen that in this. So one important point is, you see the first term is actually the volume dependent terms, which is expected because in high temperature limit, this entanglement entropy behaves as it obeys the volume law rather than the area law. So that means the more the fluctuations are coming because of the thermal entropy, not from the quantum entanglement. So actually, I see in this sense, this von Neumann entropy it's not a good measure to compute in case of the mixed state. But as we have seen in the low temperature limit, it can compute and it can tell you some information about your system and entanglement in the low temperature limit. It captures some part of the entanglement, but in high temperature limit, it completely becomes the thermal entropy. Okay. Okay, good. So now here we have plotted this the difference of these quantities where this entanglement entropy with rho equals to 0 and rho with some non-zero rho. You take the difference of these two and you plot it for different value of rho with respect to the boundary region. So here this is the boundary width. Now you can see that if I increase the boundary region, the width of the region, if my entangling region is increasing for a fixed value of rho, let's say consider the rho equals to 2, I can see that there is an increment in the entanglement, the difference between these two, which means the entanglement entropy is increasing if you increase your width for a particular rho. Similarly for another rho and for all rho, but the difference is once you fix this width, let's say you fix your entangling region and then change this density, then what will happen for a particular value of this? Let's say consider this width to be 1. For a particular one, you will see that as rho is increasing, this difference of this entanglement entropy is increasing. That means rho is enhancing this entanglement in this case. Is that clear? So you can imagine. So you fix your boundary region. Okay, it's running from, let's say, this L is a variable boundary parameter. You fix it. Okay, and then for a fixed L, you do not you change rho, and you see what happened if you vary the rho. So what you can see that for a fixed L, if you increase the rho, your entanglement entropy will increase. I mean, it's kind of increasing with rho. Okay, so this was for the entanglement entropy. Now we will compute the another measure, which is called the EWCS, entanglement wedge cross section. This is actually the dual of the entanglement of purification. Okay, entanglement of purification you can find in the boundary theory, but the dual of that was proposed by Takanagi and Omimoto, and which is the entanglement wedge cross section. What is entanglement wedge cross section? It is a good measure for the mixed state. So that's why you can see. So consider two different regions, A and B, identical regions. They are separated from some distance capital D, and the width of each is L in that way. Now you see there are these green surfaces, which are the RT surfaces corresponding to this length and this length, these two. Okay, these two RT surfaces. Now, what is the EWCS? EWCS is a surface which divide these regions in two different parts for A and for B. So now what we have to do to compute the EWCS, we need to find out the area of this external surface, which is shown here in a red. Okay, so we will use the same strategy as we did for this RT surface, the area in case of the entanglement entropy. Okay, so the A is defined in this way. From here, A is defined in this way. From here, this is minus L by 2 to D plus L by 2, and similarly B. And so in this way, and all other yi directions are, you are fixing capital L by 2, similar to the first case of the entanglement entropy. Now, because here you want to find out the area of this red surface. So this is starting from this turning point, which is the turning point of this RT surface, and ending at this point, which is the turning point of the another RT surface. So the integral limit will be, the integration limit will be from ZT D. So the ZT D is basically the turning point of this one, or for this one. And ending at the upper limit will be this one, which is the turning point of this LL, yani that means 2L and plus T. So the upper limit will be 2L plus T. So the turning point of because you are varying Z. So you are starting from a ZT, which is the turning point of the D region, corresponding to the RT surface of D region, and ending at some another point, which is basically the turning point of the whole region, which includes A, B, and D. Okay, in this way. Now you can use the similar Euler beta function here, and you will see that you can write this expression in this form here. So one immediate thing from here actually is, if you take this T very large, that means you separate these two regions very far away from each other. So what will happen? These two pieces are exactly same, and you have the entanglement wedge, which is 0, and that you can also understand from the figure. So let's say I take these two pieces and I can just move them. So what happens? These two surfaces will become closer and closer, and eventually this red surface has a 0 area. That means your entanglement wedge cross section vanishes at that point. Okay.
The physical meaning of the entanglement wedge cross.
It is the dual of the entanglement of purification. So similar to the entanglement entropy has a dual like the holographic entanglement entropy. Now entanglement wedge cross section is actually you compute the entanglement wedge cross section in the gravity side. That will be actually, you can access the entanglement of purification of the boundary. It's like if you want to study the entanglement of purification, then you can study the entanglement wedge cross section in the bulk. It also it also connected with the mutual information actually. This entanglement wedge.
So in the case of entanglement purification, we should add another subsystem to make the full system to be pure state. So do we have some other states in that picture in the dual geometry? Now we have A and B.
So we have A and B, and we want to compute the correlation between A and B.
Okay.
On the boundary side. And one of the good measures to do that is the entanglement of purification. But the problem is we cannot do it on the field theory side. But what you can do, you have the homologous surfaces corresponding to these two regions on the bulk side. So entanglement is a particular surface defined, which actually divide this region. This region is called the entanglement wedge. This region inside these two surfaces, it's called the entanglement wedge, and it is the minimal surface which divide this entanglement wedge in two separate parts corresponding to A and B.
So that means that there is some conjecture that gamma W gives us the entropy you mentioned in the language of entanglement purification.
Yes.
Oh,
yes.
I see.
Yeah, right. That's true. Yeah.
Okay.
Okay. Now you can define the low and high temperature for EWCS also, similar to, but here you have two different scales because you have two turning point corresponding to each RT surfaces. So what you can do, you can say that, okay, my first, to define the low temperature limit, this ZT, which is the ZTD, is very, very far from the horizon. But, and also this 2L plus D, the another turning point, is also very far from the horizon. So if you individually invert these relations with the boundary parameter, so then you can write, you can substitute it here, and you will end up with this result in the low temperature limit. Where again we can see that EWCS has a contribution from the correction because of the rho, and with this rho it is increasing. You see, so this rho, if you increase the rho, EWCS will increase. Here you have this second term is also plus of rho. So eventually, if you increase your rho, this will increase the EWCS. And in rho goes to zero limit, you can verify these previous results, which are exactly matching from. Okay. In high temperature limit, what we will do, we will take that, okay, our entangling, this turning point corresponding to the D region is very far from the horizon, but the another turning point is actually approaching to the horizon. I'm not taking that both are approaching to the horizon, because if both approaches to the horizon, in that case, that is the trivial case, and I will have the zero entanglement wedge cross section, because both will be, kind of overlap, and there will be no red surface between these two. So almost this EWCS vanishes there. So in this limit, again, you can invert these relations and you can substitute it back here, and you will end up with this result. So this is the EWCS for the high temperature limit, where you can see the corrections are coming, this rho dependence parts are here and here. These this A2, A0 are actually the D dependence terms, and C depends on both rho and D. Okay, and similar observation are previously reported. If you just take this rho goes to zero limit, you can extract those results actually. Okay, so here we have a plot of this entanglement wedge cross section with some quantity which we define this, the region between these two boundary regions, this capital D. So if you plot with respect to EWCS with respect to that width between these two, you will see that for different values. So okay, first for, let's say you fix a rho and you plot, you keep increasing the separation between these two. So you will see that the entanglement entropy will this entanglement wedge cross section will decrease, and after a particular time, what happens, this will be completely saturates for a particular value. For different rho, what will happen, the rate of this decrement is different. That's it. So now you choose different rho, your rate will be different, but eventually they will saturate on a similar point. Here this is plotted with respect to the boundary width. Now what you do, you fix your D, by L, and you keep change this width. Okay, so you will see that again it kind of increase, because that is from the if you remember that figures, you can see that if you increase this one, then this surface will go more and more closer to the horizon in that case. Okay, so we also know that this EWCS increases with increasing rho. Okay, so now I will come to the second part of the talk, which is related to the chaos. So what is chaos? Basically, you take the initial point and you just slightly perturb it, and you measure it later time. So what you will see, there is an exponential. If there is an exponential deviation between these two trajectories, then you will call their system is chaotic. So you know this three-body problem, three-body system, and this billiard ball system, and so they are classically chaotic. So classically, we can define that this dqt and dq0 is exponentially lambda t. So these two trajectories separate exponentially, even if you change your initial conditions very mildly. So that is the signature of the chaos. This lambda is called the Lyapunov exponent, which characterizes the growth of this separation in these two. In quantum mechanical systems, to identify the chaos, what you can do, you can compute something called the OTOC, or out of time order correlators, which basically comes from this correlation, this commutator relation, which is the square commutator. Okay, you open this one. Okay, so this expectation will here. So you open this square commutator, you will see there will be a term for these two operators V and W. What does this means actually? You introduce V0, an operator at 0, t equals to 0, and you measure the another operator W after later time t, and you ask what is the effect of insertion of that operator with W. Okay, so from here you can immediately see that you will have this 4-point function. This is called the out of time order correlator, OTOC. And this quantity is studied for example, in SYK models and in some other cases, and they have exactly shown that this is called the chaos commutator, the C, and the behavior of this C is like this. This has this kind of form for some CFTs and SYK models, etc. So why it is important actually? Because once you go to the gravity picture, so there is something called the dual of these two operators is some disturbance. You perturb your system, and that is corresponding to the insertion of an operators in the boundary side. Okay, and there you will see that that perturbation grows exponentially with time, and there you will see that perturbation, if you compute, will be exactly same behavior as this one. Then you can compare those two, and you can read out the Lyapunov exponent and the butterfly velocity from there. So this VB is the butterfly velocity, which is actually determining how this disturbance is propagating into the system. That depends on the system system to system. Okay, now one important tool to study the chaos from the holography side is the thermophile double state. What is thermophile double state? Thermophile double state is it is constructed from the two identical copies. Okay, you can take two identical copies. It is actually the kind of purification, but a specific purification where you have exactly identical copies. Malasina shows that if you, in thermophile double case, if you have two CFTs, then that TFD will be dual to the eternal black hole, where each CFT is living on the individual boundaries of this eternal black hole. Okay, so in some, you can, so this TFD state has a holographic dual, which is the eternal black hole. So this CFT is living on this side, the left side boundary, and this CFTR is living on the right side of the boundary. Now you take any system and you make it two identical copies, you can construct a thermophile double state. And that's what we are going to do here. So we have our field theory. We will take two identical copies of that. We prepare a thermophile double state. Now, because it's a strongly covered field theory, I cannot study on field theory side. So what I can do, I can study in the eternal black hole. So now what I will do is I will do a shockwave analysis with this geometry. So you just inject a very small amount of energy from the boundary. This is t equals to 0. Here you have the negative time. Here you have the positive time. These points are corresponding to t infinity and t minus infinity. You go to the infinite, this asymptotic past, and you inject a very small amount of energy. Okay, and you wait up to here. So you will see, since if you inject a very small amount of energy, that energy will propagate in the null direction, and because of blue shift, this energy continuously grows in an exponential with time. And at a particular point, if you observe it, it will be like a shock wave to you, because it is now grown so much. So it behaves like a shock wave at that point. That's why we call it the shock wave analysis. So in this, okay, sorry. Okay, so how to do that? So the question is, the injection of that energy in the asymptotic past, how to realize that in the metric form? And what is, how do you include the effect of that blue shifted energy on the geometry. So to do that, what we can do, we can write our metric. Okay, so we have the metric and we can write that metric. Let's consider this as an example of the metric. And you write, so here, this metric in terms of the critical coordinates. Okay, so you can write this one in this way here, which is in terms of the critical coordinate, where A is defined in this way. Okay, this is solution of this Einstein equation, where this is the energy momentum tensor. Now, to incorporate the effect of that null energy at t equals to 0, what I can do, I can, because I know that if I inject a positive amount of energy, it grows and it increases it shifted the horizon of the black hole. So what I will do, I will define new coordinate u that depends on in which direction I'm applying the shock. For example, in this case, I'm using the shock from in this direction. You can also do it from here. But in that case, this V will shift. In my case, I'm applying the shock wave from here, and this side will come towards the black this one. I mean towards the boundary, because the black hole horizon will grow. So I made this change here, that I defined the new critical coordinate u hat, which is the old critical coordinate plus some shift, some finite non-zero shift. Okay, here this alpha, which is a function of x and t, is basically the shock wave part, and this theta function ensures that the effect of this shock wave, because I'm applying from the one side, so there should not be any change on the other side of the geometry. So this will ensure that the change will be only in the v goes to v is greater than 0 side. Okay, so sorry. So that this geometry only changes in this way. That's why the theta function is there. Okay, and this epsilon is just to see that if you take epsilon goes to 0, you recover the without shock wave geometry. Okay, all other coordinates will be same, but I'm denoting the new coordinate with the hatted coordinate. The relation between hatted coordinate means the after giving the shock, and without hat before the shock. So only this coordinate will differ because of the shock wave, other will remain same. So they are hatted and non-hatted are exactly equal. Okay. Now I can use this shift and I can write this this metric in this way after the shift, where I can see that there are these alphas and epsilons are here. Okay, this is kind of algebra, and you can just do that. Now I will ask similar for the energy momentum tensor. You can also make changes in the energy momentum tensor, and you will end up with this new energy momentum tensor, which is included the shock wave. Now I will ask whether this metric is a solution of the Einstein equation. The question is yes, but for this modified Einstein equation with these boundary conditions. So the point is, this is a solution of this modified Einstein equation with these boundary conditions, where this T shock has this energy momentum tensor, where E0 is the very small amount of energy which you have inserted in the asymptotically passed. You insert this, and then this small amount of energy get blue shifted because of this e to the power 2 pi t beta factor, and these are actually localized. These are localized in all other directions. That's why there is a delta functions in all directions, and this is the VV component of the energy momentum tensor.
So do you still have the strings? Because you in the right.
Yes, yeah. It's on the top of on the top of this B. So there are two back reactions now. One is because of the strings, and you give a shock wave, and because of that shock wave. So geometry will, so initially we have the deformed ADS black hole. So you have ADS, we have initially the ADS black hole. We include the strings, then that's how we have a deformed ADS black hole. On the top of that deformed ADS black hole, now we consider the this shock wave, this blue shifted in.
Is there a reason you put the cosmological constant term in the Einstein equation?
In what? For what reason?
Is there any reason?
Yeah, it's okay. So see, this is in some sense it's still the ADS black hole, right? So it is, so when you have ADS black hole, you have negative cosmological constant, means non-zero cosmological constant. But this will not affect the calculation, because what happens actually when you substitute in the Einstein equation, you will see that the left side and both right side will cancel out each other. So it doesn't matter either you put it or not.
Just a comment.
Yeah.
ADCFT 対応だと、中項が負の軸を扱うんですよ。それで入れてるってやつです。はい。OK, thank you.
Thank you. Okay. Now with this solution, if I use the Einstein equation, I can, so for example, this UV component will provide me this differential equation, which is now differential equation for the alpha. This I can write. So you see, this was in terms of U and V. I can go back to my original coordinates Z and T, or yeah, Z, X and T, and this differential equation will look like in this way, which is, you can see, it is like a Green's function. I can solve this differential equation for alpha, and I can get the solution for alpha, which looks like this. Now you see this alpha is actually dual to that chaos correlator C, which was this one. Now what I can do, I can compare this alpha and that C, and I can read the Lyapunov exponent and the butterfly velocity, which is I'm doing here. So I will compare this previous solution of alpha with this C, and I will call this, I will match these two, and I will read out this Lyapunov exponent and the butterfly velocity from there.
Could you remind me why alpha corresponds to the chaos correlator?
Yeah, so in the field theory side, this chaos correlator is basically you insert some operator V, and at later time you measure this the W operator. Okay, you can also do that with the without square commutator, but that will be kind of the response. And when you take the average, there will be some cancellations. To avoid that cancellations, you need to, I mean, people they consider this square commutator. And for they proved that for SYK models and some other cases, it is exactly the C function. This alpha is actually the C from the bulk side.
And where was alpha originally? So
It was in shift in U, yeah, here. U goes to U plus alpha. And the form of this alpha was here, the solution of this equation.
Okay, so that is a result of the equation of motion.
Yes.
Right? So, I see. Yeah, okay.
Now, after this, I'm just making some comparison and writing this Lyapunov exponent, the butterfly velocity. Now, you can see that one immediate point is that if I directly take B goes to 0, so this B is now the previous string density. If I take B goes to 0, then I don't have this part. And this part is exactly what the people have, obtained for the ADS black hole case, D plus dimension. So if I plot this one, this quantity, this butterfly velocity with respect to the temperature, I can see that if for B equals to 0, it has a constant value, which is actually the butterfly velocity for the ADS black hole. Now, the effect of B, if I turn on B, then for one distinction is, if you go for a very low temperature, you cannot distinguish the effect of B. You cannot see whether one value of B and the another value of B have two different butterfly velocities, because you can see they are converging to a particular point. So for a very low temperature and even for a very high temperature, they are saturating to the same value. But you can distinguish this effect of this B, you can see in the intermediate range. So in the intermediate range, you can see that as my B increases, the butterfly velocity decreases. And for B equals to 0, it is maximum, which is expected because more B means more number of quarks on the boundary side. That means you have more number of degrees of freedom. Now, if you insert some operator, that information will propagate into the system. And if there are large number of quarks, then that information will lost more rapidly. And that is what the butterfly velocity is suggesting. That means you can conclude that if you have more B in the system, that means your system is more chaotic. It will do not allow the propagation that fast. It try to stop it, which is means your system is now became more chaotic rather than your previous one.
Okay, this sounds somehow counterintuitive in some sense, because if the system is more chaotic, then a small deformation around here should propagate faster.
It actually that propagation lost more faster in some sense, right? Scrambled. You cannot recover the initial state.
So, okay, since I'm quite ignorant about the butterfly velocity, but
Yeah.
okay, some people say that if butterfly is here, then small butterfly changes the climate on the opposite side of the
Exactly.
So, and I guess that the butterfly velocity is how that this kind of effect can propagate to the other side on the.
Yeah. So butterfly velocity is how that that propagation is propagating. But if your system is chaotic, that will try to scramble that information. It will kind of
Propagation should be suppressed.
suppressed. Right.
That means that velocity should also smaller in that case.
Yeah, exactly. That's why it is highest for the ADS partial black hole case, because it takes more time to scramble the information. If your information has more time to scramble, it will reach more. I mean, in some sense, you can say it will propagate to more.
Okay, so then I'm confused because suppose that the butterfly velocity is exactly 0. This sounds that there is no chaos. Am I right? Any signal can affect any climate in the different places. So yeah, I agree that if the things are more scrambled, then perhaps the butterfly propagation should be suppressed. I agree with you. But on the other hand, if naively, I can say in the opposite way. Yeah, so this is why I'm confused about that. But
Okay. Well, what is here is actually as this B is increasing, that means number of degrees of freedom are increasing, and that making the butterfly velocity for a particular temperature less. That means now to access that information from some other point, you have less time. Okay, I have to explain it. The point is you choose some point, and this information will take some time to reach at that point. And there is a time called the scrambling time. So scrambling time means once you cross the scrambling time, you cannot recover the initial state. You don't know, I mean, it's completely lost. You don't know where you came from, like that. So in that sense, if there is less butterfly velocity, it will take more time to reach that particular point. And if that time is greater than the scrambling time, you do not have I mean, then you will say that, okay, system is more chaotic because now it is completely scrambled. But it can happen that for a particular system, your this velocity is so high so that the information can reach you before the scrambling time. So in that um, in that way you can access the information of the system. So in the comparison of these two, you can say that okay, the first one for which the butterfly velocity is larger, it was less chaotic because the information was not get scrambled. But for the another case, because butterfly velocity was slower, and that is how you are getting the information, and it has enough time so that the system can scramble that information and you will lose the information. So in that sense, it is. Yeah. Okay. So yeah, we have discussed these points. So butterfly velocity is 0 for, butterfly velocity for B equals to 0 is constant, and for all other non-zero values, it saturates to these points. And we can see the difference with respect to B for the intermediate range of temperature. Okay, so in the next part, what is there actually? Now we ask whether if you have the TFT state and you consider one region in this side and another region on the other side, and you ask what is the correlation between these two. So a good measure to compute is the mutual information, which is defined in this way. So this is the entropy corresponding to region A, entropy corresponding to region B, and the entanglement entropy corresponding to A and B, A union B. So this is how we define the mutual information. So we consider this picture. Sorry. So here, so okay. So again, you consider two regions on two different CFTs. So now this individual surfaces SA and SB we have computed in the first part. So they have the same value. So if you take the identical, it is twice of one and minus this quantity A and B.
Excuse me, what mean the entropy of the A and B?
What is the A and B? Okay, if you want, so okay, you have two regions A and B, and you ask how much these two subsystems are correlated with each other, how much entanglement they have. That means if you measure one subsystem, how much information you can access from the other for the other. Okay, so that is the meaning of the entanglement between A and B. So mutual information is a quantity which is used to define these correlations. It is the important property is that it is actually free from the divergences as the entanglement entropy this divergence appear in the entanglement entropy. Okay.
Yeah, I can make some more.
Yeah.
So suppose that A and B are completely independent each other. Then the entropy of the total system should be just a summation of entanglement of A and entanglement of B. Okay, then the total entanglement, total entropy should be just a summation. Then the I should be 0, right? A plus B minus
SC plus SB.
Yeah, but if they are they have some communication or there is some interaction between them, then that quantity cannot be 0. So this is how that function measures how these two things are talking each other.
Yes, yeah, exactly. So there are a few properties for this mutual information that it cannot be negative. So that's why we always stick to the case, because this A union B has two different choices. Either you can take individual sum of these two, or you can connect these two surfaces. So usually we will restrict to the positive non-zero mutual information. So our choice will be always this A connecting to the B and the others A is connecting to the B. I mean, the end points of these A and B with each other. So we define this. So A and B we have already computed in the first part. So here we will only focus on this A union B. So because now I have the two different sides A and B on this eternal black hole. So to get this A union B, I have to cross through the black hole. And that's why I'm calling it the wormhole surface, because it is passing through the horizon and connecting with the another point of the A of the B. So my wormhole surface will be the union of these two 1 and 2 surface. The one is A connected with B and the next part of the A connected with the B. Okay, so I define these two surfaces gamma 1 and gamma 2 in this way. Okay, and then I follow the similar I compute the induced metric and use this the same extremize this thing and compute this conserved quantity as I have done for the entanglement entropy, and I will substitute back in this formula. So this is same, so twice of this one, and for this one I already have computed in the first part. So I will substitute it here and I will get this expression for the mutual information. You can see from the individual SA and SB, I have this 0 to ZT here. Because I have two surfaces and two SA and SB both are identical, so there will be a 2. Okay, there will be some 2 factor, and this 2, since this is that there will be 2 already in the beginning, and then there will be this 2, that's why that will make it 4. And here I am computing this limit is from 0 to ZH. So basically what is happening, this gamma 1 surface is from here to the another side, and the other surface is from here to the another side. So this midpoint is somewhere is the horizon. So what I will do, I will compute the integration from 0 to ZH and just multiply it with the 4, because this part, and these two parts are symmetric, exactly same. So that's why there will be a factor of 4. And when I write this A over 4G, that 4 will cancel out with this. That's why there is no 4 here now. So that will comes out and it totally cancelled from each other. So here the limit is from 0 to ZT, and here it is from 0 to ZH, because this is the wormhole case, this one, which is exactly passing through the bifurcation point of the black hole. Okay, I can numerically plot this this expression, and I will get this this plot. So here you can see, as I increase, so for a fixed t, as I increase the width, after a particular value, this mutual information start increasing. That means correlation. But before this initial value, or the mutual information is 0. That means, so this L, the boundary region. So to get a non-zero mutual information, you have to cross a particular value of the boundary region L, which let's call it the critical width, critical L. After that critical L, if you take the value greater than that critical value of L, you have the non-zero mutual information. Otherwise, for all values less than the critical value or including the critical value, you have the zero mutual information. And that is because of the choice of the RT surfaces of A union B, what just we explained, that if you have some correlation, then they have the connected surfaces. Now that critical value of L is now affected by this B, because you can see the critical value of for B equals to 0 is this one. So if you go beyond this line, beyond this point, you have the zero mutual information. No correlation you can have between these two regions. But what you do, you increase, instead of increasing the width, what you can do, you can increase the B. And still you can find that for a particular value of B, for particular value of L, you have a non-zero mutual information. And after that, it less than value of the critical value, it is 0. So basically what is happening, this B is kind of reducing your critical width. That means this B is trying to increase the correlation between these two regions. Okay, because initially you fix your, let's say you have B equals to 0. Okay, for B equals to 0, you have a restriction that to have a non-zero correlation, you have to take the boundary region greater than a particular L. Otherwise, you do not have any correlations. But what you do, you just stick to that region, and instead of increasing your L, you increase your B. And now you have some non-zero correlations. So in some sense, it is kind of decreasing this critical value of this L. So now you can have the non-zero correlations even if you are below a particular critical value of with respect to B equals to 0. Okay, so the conclusion is that now you have a non-zero correlations even for a smaller bit, which initially you don't have when you have b equals to 0. Okay, so this now we in the previous part we have seen that there was a shock wave we introduced and we computed. In this case, that shock wave affects the geometry. So now because of that shock wave, this effective geometry will look like this. We again compute the same thermomutual information. So in the previous case, that this mutual information is called the thermomutual information. We call it the thermomutual information, or two-sided mutual information, whatever you want, because here two regions belongs to two different parts of the CFTs, which are on the left and right side. Now we will compute the same thermomutual information, but now in presence of the shock wave. So you introduce a shock wave, now your geometry will again change, which became like this. This effective geometry is like this. Then you choose two regions, one is here and another is here, A and B, and you have the connected surfaces between these two, and you ask what is the correlation between these two regions now. So then again you have to compute this area of this surface, and that will tells you the what is the correlation between these two. So to find this, we define the mutual information in this way, which is I0. So basically mutual, it has the same definition, but slightly modified, because now I have introduced the regularized entropy, which is basically the difference between entanglement entropy with alpha minus entanglement entropy without alpha. Okay. Okay. So to find this regularized entropy, I have this kind of embedding where gamma 1 and gamma 2. So basically this you can it's like surface is coming in this way, and one surface is gamma 1 and the backside surface is gamma 2. Okay. So sorry. Okay. So you again write the similar way. You define the induced metric and you write the action in this way. And you say that, okay, there is the conserved quantity corresponding to the T, because there is no T dependence, explicit dependence of T. So you have the conserved quantity in this way. This R is the radius here. Okay. Now what you can do, you can break, because this is the whole integral from one side to the another side. So to compute this one, what you can do, you can break your regions in different way. You come from boundary z equals to 0 to horizon. Then from horizon to some, okay, so let's come from this side. So you come from boundary to horizon, then horizon to Z0, okay? And then Z0 to again this horizon. And then rest of thing is same as this one. You just multiply with 2 and that will be same. So that's why this limit is here, you see. Now from 0 to ZH, from boundary to the horizon, and from ZH to Z0 point, which is this one, ZH to Z0, because this one and this one are exactly same. So you just multiply with 2. You do not need to write the expression again. So that's why there is a factor of 2. So now this will be the entanglement entropy, this A union B in presence of alpha. Now why it is different from, you see, so in this time you can see this region is actually inside the black hole. And without shock, if you see this figure, this one, without shock, this was the picture. So without shock, you see, this is just passing through a single point. So the surface, this dotted surface, it is traveling less inside the black hole. But this time, it is traveling more inside the black hole. So in some, you can say that, okay, now your surface is traveling more inside the black hole, which means actually this wormhole, which was initially a point like, is now increased in the length. And now to go from one side to the another side, you have to travel through the wormhole. So your external surface has to be more longer. So in that case, in that sense, I can say that, okay, this regularized entropy will increase because this surface is now has to travel more inside the black hole, and it became the area became large. Okay. So now the question is where is the effect of the shock? So the shock effect is controlled here in this Z0. So in this in this you can see that if I give a more shock, then these two will this horizons will go closer and closer to the boundary, and this picture is became more and more tilted. This wormhole length became more and more. Okay, so basically in that sense you can say that this Z0 surface will move towards the singularity in this direction. So in some sense this Z0 is tuning this shock. You can tune the shock using the Z0. So in our expression we have this Z0, but now to see the connection between this regularized entropy and the alpha, we need to express this Z0 as a function of alpha. To do that, what we will do? We will use this Kruskal coordinates. We take their variations. So we can take their variations from boundary to the horizon, then horizon to the Z0. Okay, and you will get this relation, the relation between Z0 and alpha in this way, where these eta1, eta2, and eta3 are these integrations. Now you see you can plot alpha with Z0. You can plot this S regularized with Z0, right? And you merge these two and you can get the relation between S regularized versus alpha. Okay, so now so we have plotted this S regularized A union B for different values of B. So one immediate thing is you can see that as log alpha, so plotted with the log alpha actually, because you can understand it is like the plotting with the time, because alpha was e to the power 2 pi by t. Okay, so this alpha, so if you increase the alpha, log alpha, then this regularized entropy increases. And since this regularized entropy was in the minus or in the mutual information, it was I equals to I0 minus S regularized. So if this S regularized increases, then it decreases the mutual information, which is depicted here. Okay, so for different value of B, you can see if I fix my alpha, if I take a constant value of alpha, and I will see the variation, if what is the effect of this B on this for the fixed alpha, then I can see that if I keep increasing alpha, this regularized entropy will increase, which was actually also observed in the previous case where we explicitly have the rho dependence in the entanglement entropy formula. Okay, now I can substitute everything in the mutual information formula, and I can compute the this mutual information, this ratio of mutual information of alpha non-zero with alpha zero mutual information. And I can see that as I increase the alpha, that means as I increase the shock wave, this mutual information, the ratio of these mutual informations is decreases for, and after a particular alpha, it vanishes completely. But what happens if you increase the B? So the effect of B is the rate of this decrease is becoming more and more. So if you turn on B and you increase B, your correlations between these two sides are lost more rapidly, even for a smaller shock. Okay, so in some sense we can say that this B is making the system more chaotic, because now these correlations are destroying more faster than the zero case. Okay, so you can say that, okay, these are some critical values of alpha below which you have some non-zero correlations, but after that you do not have that non-zero you have zero correlations, and this critical value of alpha is becoming less and less. That means you need to apply smaller shock even if you have the larger value of this back reaction here.
I have one question. So I think that the Hawking temperature depends on the value of B, I think.
Yes.
So are you fixing the value of the Hawking temperature when you compare different B's?
Yes. So there are three parameters. Okay. So in the temperature equation, you have temperature is a function of ZH and B. So what you can do, you can fix one of them and to express the another. I mean, for example, you can fix t, then your ZH and B will vary according to each other, right? So that's what we did here. So we just take T fix and allow ZH to move. And then if you fix B also, then your ZH is also fixed.
Yeah. So if I say that, okay, if I want to say that the B makes the things more scrambled, then okay, I want to fix the temperature as a constant value, because if the temperature varies, then the people may
Yeah.
say that, okay, it's just not because of B, but
It's because of
right.
yeah.
So we have to fix the.
You have to
This
fix
is
it.
why I asked you.
Yeah,
So
that's
you
true.
have to-
That's true. Okay, good. Okay, so let me summarize the results. So what we have observed in the first part, that the entanglement entropy increases with the quark density, or in the bulk size with the string density. And also the increasing behavior of EWCS was reported. We have seen that the quantities which characterizes the chaos in a system for this butterfly velocity and the Lyapunov exponent, they are also get a contribution because of this back reaction. Okay. And to see how this two-sided mutual information, that means the correlation between two copies of the causally disconnected theories, which is the thermophile double, how these correlations are affected with this back reaction parameter, and how they behave even if you vary your B. Okay, and we observe that it increases, and this mutual information disrupted more rapidly if you have more B, and we concluded that your system became more and more chaotic because of this back reactions. So here are some future directions. So we are planning to compute this EWCS in the shockwave geometry, because you can also compute the EWCS for single-sided in one-sided theory. You can also compute it in the two different sides. I mean, you take one in this side and another on the two different disconnected boundaries, and you compute. So you will see that whatever crosses the horizon, it is affected by the shock wave. So we want to see how this EWCS of this two-sided EWCS get affected because of the shock wave. What happens to that? Another possible direction can be the photon production rate of the back in this back reacted model. I mean, this point I actually recently come to discuss with in the winter school actually. So I don't have much idea, but I mean, I think this is one of the possible thing which I talked about few people. Okay. Next, we are trying to do the entanglement negativity for various excited states in two dimensions. We basically we use the replica trick, and we try to see whether we can compute this entanglement negativity by forming a thermophile double state for the excited state from the CFT side, not from the bulk side, from the CFT side. Okay, thank you. So that's it.
Okay, thank you very much. So any questions or comments? So do you have any idea to apply your story to the real QCD or some Cockburn plasma?
Yeah, I'm looking in that directions actually. So the people have computed this entanglement entropy. They used it as an order parameter to distinguish the phases in QCD. And I'm wondering whether one can use this chaos. I mean, you compute the butterfly velocity and use this thing to basically distinguish these phases there. So yeah, I'm thinking in that directions, but I think if for particular interesting models, one can compute this, because there is something like you can use the holographic QCD thing, and you can use all these techniques there. But whether they will be interesting or not, that depends on the results actually, and what else, what you can extract from these calculations.
Okay. So any other questions? Comments? The audience on the online, actually only one person here, but maybe no.
I have one question.
Okay, please.
I apologize in advance for my poor English. You examined the changing entanglement entropy because of the resistance of cork in a finite temperature system. Can that entanglement entropy be considered as a changing thermal entropy, or should it only be understood in the context of entanglement?
So here actually, I mean, it is only on the context of the entanglement.
Oh, I see.
Right. Sorry. So by entropy, you mean the thermal entropy, right?
Oh, no, entropy. No. Yes, I see.
So actually, if you see this in the, if you take the high temperature limit, so there actually the most of the fluctuations are coming from the boundary regime, and that is basically yeah, you can say that this entanglement entropy is actually follows the volume law rather than the area law. So it's actually the thermal entropy in the high temperature regime, you can say. I mean, there is a transition from area law to the volume law. But yeah, I mean, that transition is not explicitly, I mean, observable, like it's some particular limits to different limits.
So in general, it's a kind of mixture between the.
Yeah, right.
Okay.
Yeah.
At the finite temperature.
At finite temperature, yeah.
I see.
Thank you for your answering.
Yeah, thank you.
Okay, so any other questions? Okay. Okay, let's thank the speaker again.
Thank you.